Okay, in this video we're going to look at a new class of functions called exponential functions. And the idea is, earlier in the semester we looked at things like quadratics, polynomials, things like y equals x squared. Now we're going to look at functions that say like y equals 2 to the x. And we just want to be clear on the difference. Here, for the polynomial, the quadratic, the thing I plug in is the base, the x. It changes. The power is always squared. It never changes. For exponential functions, the base 2 always stays the same. It's actually the power that changes. Just make sure we understand the difference between those two. So we'll stick with the one I just wrote. Y equals 2 to the x. If we want to understand that, generally speaking, the first thing we do is graph it. So let's do a graph. And if we're not entirely sure what it looks like, we generally draw a table. So we'll have x and we'll have y. And I'll just plug in some x's. -2, -1, 0, 1, 2, 3. And we'll find the associated y's. If I plug in -2, y equals 2 to the -2. Negative exponents, we know, flip my problem. That becomes 1 over 2 squared, which is 1/4. So at -2, I get 1/4. If I plug in -1, I get 2 to the -1, which is 1 over 2, which is 1 over 2, 1/2. So at -1, I get 1/2. If I plug in 0, I get 2 to the 0. We remember our rules of exponents. If you raise anything to the 0, you get 1. So at 0, I get 1. If I plug in 1, I get 2 to the 1, which is 2. If I plug in 2, I get 2 squared, which is 4. If I plug in 3, I get 2 cubed, which is 8. So at 1, I get 2. At 2, I get 4. At 3, I get 8. And clearly, as x gets bigger, this will just get bigger and bigger and bigger. Over here, these are not spaced out very well. I'll go down like this. And the question is, will I ever hit 0? But if you think about it, as I go this way, my exponents are negative, which means I'll end up getting 1 over 2 to some power, because the negative exponent will flip. So I'll always get a fraction 1 over something. Fractions are only 0 if the numerator is 0, which means that's never 0. So instead of hitting 0, I'm just going to approach it. I'm going to have a horizontal asymptote right there, approaching 0. And there's the graph of our exponential. Now, we're going to mess around with that some more. But first, just so we kind of understand how this goes, suppose I look at a different exponential. Now we'll use y equals 3 to the x. I'm not going to draw a table here. We can kind of do this quickly. If I plug in 0, I get 3 to the 0, which is 1. If I plug in 1, I get 3 to the 1, which is 3. If I plug in 2, I get 3 squared, which is 9. Clearly, this is going to just keep on getting bigger and bigger and bigger. If I go to the left, if I plug in -1, 3 to the -1 is 1 over 3. So at -1, I get a third. If I plug in -2, I get 1 over 3 squared, which is 1/9. And then again, for all the negative numbers, I'll end up getting 1 over something. So I'll get smaller, but I'll never hit 0 and I'll have a horizontal asymptote. Point being, this is the graph of an exponential in general. Horizontal asymptote approaching 0. Always goes through 0, 1. Because anytime I plug in 0, I get something to the 0, which is 1. And then it shoots off to infinity really quickly. Exponential growth. One more, though. Suppose we have y equals 1/2 to the x. Again, if I plug in 0, I get 1/2 to the 0. Anything to the 0 is 1. If I plug in 1, I get 1/2 to the 1, which is a half. If I plug in 2, I get 1/2 squared, which is a fourth. And now this graph actually gets smaller. If I plug in -1, I get 1/2 to the -1. Negative exponents flip things, and that becomes 2. And at -1, I get 2. And now we can see this will go up. Which means when we draw these exponentials, there's really only 2 graphs I can possibly get. I'll always go through 0, 1, and I'll either look like that, or I'll look like that. It's entirely based off of your base right here. If your base, call it A, is greater than 1, you'll have exponential growth. If your base is between 0 and 1, like a half, you'll go down, you have exponential decay. But now, in the same way that we know the graphs of the quadratic and the cubic and the absolute value, now we have graphs for exponentials. Always go through 0, 1, and either shoot off to infinity or go down to 0 and flip everything. I'm not going to do it here in the video, but essentially what that means is, earlier in the semester we did transformations of graphs, and we said once you know a basic graph, quadratic, cubic, absolute value, then you can apply the transformations. The same thing will apply here. If I want to graph y equals 2 to the x plus 3 minus 4, that's an exponential. Base is bigger than 1, so it looks like this. Plus 3 inside the function will shift me 3 to the left. Minus 4 on the outside will shift me down 4. So I take this graph, shift 3 to the left, down 4, and sketch my new graph. I don't want to take the time to go through those on the video because we did so many of them before. But just be aware, all of your transformations work the same. For right now, though, there's a lot of exponential functions clearly. I can make my base whatever I want it to be. But as it turns out, there is actually a special exponential. Y equals e to the x. It's the number base e. If you're not entirely sure what that is, just look at e to the 1. Throw it into your calculator. If you throw it into your calculator, let me get mine. Let's see. Find the e to the x button. There we go. There's the e to the x. Ooh, I hit the wrong one. Plug in e to the 1, 2.71828, etc. 2.71828, and then it keeps on going. That's the number e right there. It's an irrational number in the same way that pi is. It's a non-repeating, non-terminating decimal that goes off forever. But it's actually really important in the same way that pi is. That's why we give it that name. If you actually care, this is pre-calc in calculus. There's something you learn. The limit as n approaches infinity of 1 plus 1 over n to the nth is equal to e to the x. Essentially, this is the definition of the exponential function. But that's like a calculus thing, so you don't have to worry about it. But the short idea is that's an exponential, and it's a really, really important one. In the real world, a lot of things grow exponentially. We have exponential growth. And a lot of them can be modeled by an exponential function, and we use that one right there. But if all of that seems a little bit confusing and weird, to a certain extent it doesn't matter. That's an exponential. We know it either looks like this, or it looks like that. Entirely based off of the base. But we said e, the number, is 2.7. That's a base bigger than 1, which means I know immediately my exponential graph for e to the x looks like that. Still has to go through 0, 1 because it's an exponential. But other than that, while it may seem new and a little bit strange, all we really care about is it's an exponential, its base is bigger than 1, I know the graph, and I'm good to go. I can do all my transformations on the graph of e to the x because I know what the basic graph looks like. We're actually going to spend a lot of time, the entire rest of the semester, going through exponentials and things slightly different. But for right now, we just want to make sure we have kind of a basic understanding of what exponentials are. They have a fixed base and the power changes. And in particular, this exponential right here, e to the x. The last thing I'll point out for you guys to kind of think about and ponder as we start working through this. In the last video, we were talking about one-to-one functions and inverses and how to find them. And if we look at the graph just right here, we said to determine if something is one-to-one, we use the horizontal line test. If I do it here, a horizontal line will only touch that graph once, which means exponential functions are all one-to-one functions. According to what we did in the last section of your book, that means they'll have inverses. And logically, if these exponential functions are important, and they are, they have a lot of applications in the real world, e to the x, things like that, and we're going over them because they're important and they have applications in the real world, and they're one-to-one, which means they have inverses, then it would stand to reason whatever their inverses are also important. That's actually what we're also going to spend the rest of the semester going over. These exponential functions and their inverses.